Okay, small problem with the technology. So, in the meantime, what can we do? Okay, now the first thing to talk about is the proportion, of member states of the UN in Europe, because I found out there's 193 states in Europe, and how many, no, not in the UN, right. So how many are in Europe? And it turned out, okay, let's see, the people who were given, half of you were given 10 and half of you were given 60. And the median guess, that means the one that's halfway along, for these was 24%, and for these I think was 40%. Okay, so remember we talked about the wisdom of crowds? The wisdom of crowds. Now, if you're a wise crowd, then on average you should get the right answer. So in fact, how many states are in Europe? The correct answer is, ba-ba, it's 48, which is 25%. So the ones who were given the 10 were almost dead on average, because they're almost exactly right. But the 60 really biased people upwards. Just being told this stupid number, this what's going on? Yeah. You see, you were influenced, you were badly influenced just by being told this number at the beginning. So the practical, I've typed the data in, and it's in a file, undata.csv. So the practical is to take the two groups of people, draw a histogram for one lot, histogram for the other, and to test whether, although the medians are different, are they significantly different, the two groups? Is the mean judgment significantly different? Okay, they are different, but there's a lot of overlap on the histograms. You know, it's not like they're completely split. So, and because that would then definitely prove that the number you were given influenced your opinion, because it was randomized. We know because it was randomly done, so that we can done a proper clinical trial of this treatment. Okay, so that's the practical. I'm not a guest user. Login. I need a lot of help. I need constant care and attention. Okay, so the other thing, today we're going to do a range of things before going up to the practical. And some of that there'll be some sort of technical things. But also I'm going to get you to stop at one point, and I'm going to hand out a few articles, newspaper articles, one from a South African newspaper, one from a British newspaper, and one graphic, and ask you to spend some time looking at these and thinking about some questions that I'm going to put up. So this is about looking at statistics as they're reported in the news. Okay, we're nearly there. I'll be there in a minute. Okay. So there should be the UN. There's the UN data, which is all your opinions that have gone in. And then we want, where are we? Stats actually fun. What have I done? Shush. What? Oh, I was watching something about Rio de Janeiro. Okay, right. We don't want to watch about Rio de Janeiro. This is what a chaos this is. Let's calm down. Let's keep calm. Let's just keep calm, and see where we are. Download to the desktop, and then we should be all right. Okay, now. Let's get a grip. Oh, look at my banking details as well. some of them. Don't look at me. Okay, right. Here we are. We're ready. We're off. We're off. Yeah. Okay. So, oh yes, yeah. But I wanted to, this wisdom of crowds, I wanted to tie that in slightly with what I said about surveys yesterday, is that it'll only work if there's no systematic bias. You know, the wisdom of crowds, like the beans in the jar or this question, only works if there's no systematic bias, and so the average opinion should tend to the truth if you ask enough people. Now, that's what happens in a good survey, and it sort of happened here, but it doesn't always happen. So these are the same things. We're trying to avoid systematic bias. Okay, I'd just like to go back to this one, just because it uses this as an introduction to some of the ideas of regression analysis, of adjusting for other factors, not just looking at correlations, but going beyond that. Now, in the results, if you remember this study, they had a group of people, about 1,000 people were controls, the control arm, and then they had a group of about 600 who were given $10 for being tested and being negative every 4 months, and a high value who were given $20 every 4 months to be tested, and they only got the money if they were negative for a set of sexually transmitted infections. And the crucial thing they focus on is this number here, which shows that after 12 months, 126 people in the control arm had the infections. And after 12 months, there were 57 in the people who were paid had the infections, which is, instead of 12.1%, there were 9.7%. And so they took the ratio of 9.7 to 12.1 and said the ratio is 0.8. In other words, there's essentially, it looks like 20% fewer people have infections in the group given the bribe, the cash incentive. Okay, and then they put a confidence interval around this 0.8, but it includes 1. So they can't say, oh, this is statistically significant. Okay, so that's what I've just said. The control group had this many infections. The $20 group had that many infections. They take the ratio and call that the relative risk. So instead of taking in two groups the difference in the probabilities, we've always looked at P, we might call this P control minus P $20. We've looked at differences, but they take the probability in the $20 group and divide it by the other one to get a relative change. So they can say this is 80% of that. Okay, now it's actually quite difficult to put a confidence interval around a ratio. You need special functions to do that. It's not a simple calculation in the way that we've done calculations so far. So they use a special function from Stata, we're using the package Stata, and to produce an interval around that ratio. We could do something very similar, looking at the differences. If we put this data into R and do a prop test comparison, we can obtain a 95% confidence interval for the difference of the proportions of minus 0.8% to 5.6%. So again, as we could guess, we don't get a significant difference. This confidence interval includes 0, the no difference, and the p-value is greater than 0.05. So we can't conclude from this data that it's worked. It could be just chance. It could be just lucky that the group that were paid did a bit better. It's not a significant result. So that's a bit disappointing. But then they say, well, maybe the groups differed a bit at baseline. Because although they were randomly chosen and they put their hands in and pulled out a ball and decided which group they would be in, maybe they actually differed. And so what they do is do a regression analysis. And this is a way of adjusting for other factors, not just looking at one factor at a time, but looking at multiple factors. Now, in the baseline, they did differ a bit. This is the control group, and this is the high value group. And they differed a little bit. Where do they differ? They differed a bit in the high value group earned slightly more. The education was pretty similar, very low levels of education. The high value earned a little bit more. What they did, what I hadn't realized, is that the actual, the prevalence of these conditions was very high at baseline. So they're actually looking for the prevalence to go down of these conditions because they're all being treated. So it's a slightly odd study. The more I read this, I'm actually not sure this is a very good example of statistics. I'm not sure they've actually analysed it very well. I don't think it's how I would have done it. So it just shows that you can't always, everything that's published isn't always perfect. So the point is that they say these people might have differed slightly. How can we adjust for these other things? So now we're going to talk about adjusted estimate and just briefly talk about multiple regression. And just because, we haven't, in this short course, we haven't got time to go into detail, but it's just something that, in a way, you should know, or at least be familiar with the ideas of it, so that the language is there. Okay, let's look at a continuous outcome. Why? So like height or your hand span, some sort of outcome variable which we might assume has got a continuous value, not a count or an event. And we got some treatment. 0 if it's the control group, and 1 if it's the new treatment. So some people are getting the treatment and some not. But there are these other factors, and these are called confounders. Confounders. Confounder is something that might mess up the result, because it might be correlated both with the treatment and the outcome. So in epidemiology, yes, I've been looking at this. People who eat more, in America, people who eat more meat tend to die earlier. People who eat more red meat it's really bad. Well, it looks like it's really bad for you. But so people who eat more meat actually have worse health in America. Okay, that sounds, whoa, that meat must be bad. In America, poorer people eat more red meat than richer people. Very interesting. It's just complete opposite to what you might think. The poor people eat more red meat because they eat, there's burgers in the McDonald's and other places. They eat more meat than richer people. So maybe people are dying earlier, not because of the red meat, but because they're poorer. Because we know that poorer people have worse health. It's just true. Just is the fact. It's just not good being poor. Don't be poor. That's the first the first advice for good health. You can advise about exercise and smoking, drinking. The first rule is don't be poor. That's the best advice of all. But of course, that's more difficult to advise somebody to say. So don't be poor. So there's an example of a confounder. Income is a confounder because it's related both to red meat and to health. And the way people get around that is to put them into the equation. You build an equation for how big you expect your result to be as a function of the treatment. There's some constant value, and then some function of the treatment, but then you add these extra things in to adjust for all these other factors that might be important, and you want to sort of get rid of. You're not interested in these. You just want to stop them influencing the relationship. Now the trick is, by building this nice linear regression, nice formula like that, for the expectation, I think you'll see that if for the group, if you've got a person with some vector of confounders x, and you give him the treatment, his expected result will be A plus B, because T is 1, plus all this lot. And if you didn't give him the treatment, if he picked the wrong bull, or the bull, his expected result would just be A plus this lot. So if we subtract these, we see that B is the expected result, the difference in the expectation from getting the treatment for fixed x, regardless of what x is. Whatever x is, B is the expected result. And so that's known as the treatment effect adjusted for this In other words, it's the effect, assuming these are fixed. So it would be like, for people of the same income, if you knew that the people who ate more red meat were less healthy, now that would be good evidence, because you've controlled or adjusted for income. Okay, so is that okay? So the idea, nice, sort of fairly basic stuff. And the point is that the functions in R and elsewhere just allow you to do this really easily. So let me just show you an example. We looked at handspan and gender. And if you use this function LM, handspan twiddles gender, it tells you that this is the average handspan. Actually, this is the handspan for women. And for men, it's 1.66 centimeters wider. So if you if you think of gender as a treatment, it's a bit strange, isn't it? Anyway, think of gender, whether you're male or female, as a medical treatment. Then we'd estimate. You see what we're doing is the expectation of handspan equals A plus B times whether you're male or not. So I could write that as gender equals male or something like that, some sort of indicator function. If your gender equals male. So that B is the effect of being male. So if you're, for females, that's their average handspan, and for males, it's that. And that's the model that the function LM fits. It just fits a linear model. That's what LM stands for, linear model, meaning it's just additive. LM equals linear model. Okay, so that's all right. Then it's really easy. If we want to say, well, is this just because men are taller that they've got bigger hands? In other words, if we took a man and a woman of the same height, would we expect them to have different size hands? That's a reasonable question to ask. Or is it just something about men that makes them great big hands? Nothing to do with just how tall they are. So really, I had no idea what the answer might be. That's quite an interesting question. I think interesting. Well, maybe it's not very interesting, but never mind. Can't try and be interested. It's really easy. All you do is put plus height in there. So now we're just fitting the model plus C times height. We're not interested in this C particularly, but we just want to know whether this is still positive, not zero, when we allow for height. And that's all we do. Really easy peasy. And we find out, whoa, it's still there, 1.16. So now, adjusting for height, male handspan is still 1.16, 1.6. Yeah, that should be 1.16 centimeters wider than females. So men of the same height as women, on average, will still have wider hands. Is this a significant difference? Well, we can ask for confidence intervals, and we find the confidence interval around this goes from 0.48 to 2.84. Yep, it's not zero. It is a significant difference. So we have found in this class this incredibly important scientific discovery. I don't think you can write your essay on this. On that even the men and women of the same height should still have different size hands. So is that okay? It's really quite an important sort of idea, and it worked quite well with this data. Okay, are there any questions on that? All right, good. We're going to the next thing. We're not going to do these, but I just want to illustrate the fact that this is what's often done in practice, especially in a lot of medical papers, because most medical papers don't have a continuous outcome. They're almost always counting things. They're counting infections, or they're counting events that happen. And so we tend, in medical papers, you use all the time Poisson distributions and Bernoulli distributions and binomial. You don't actually use normal very much at all. In my medical work, medical statistician for years, I very rarely use a normal distribution, because it's all to do with events, what happens to people, not not measuring something on somebody, except maybe in CD4 counts in monitoring HIV. Then you get a continuous measurement. So if we have a Poisson outcome, we've got mean theta. Now the problem is that theta is positive. And if we built a linear model on theta, we'd have to make sure that this always was positive. It's quite difficult. You can do it. You can build regressions which are always going to be positive. Much easier to build a linear regression on the log of theta. So we transform theta from, theta is, between 0 and infinity. But we transform it to log theta, so we got the whole real line from minus infinity to infinity to play with, making it much easier, more appropriate to build one of these models. And this is the trick always used for this. You've got a transformation, log theta, and then you fit this. And there's lots of software to do it. You can't do it exactly. You can't do it using a nice formula. Yeah, it's only recently people have been able to do this because you need iterative methods to get the maximum likelihood estimates. You can't write down a formula for the maximum likelihood estimates. It's really horrible. The computer has got to estimate these numerically. It's a real shame. You just can't write down the formula for them. It's too messy. So the computer will eventually come up with estimates of these and 95% confidence intervals based on the asymptotic covariance matrix like in Fisher information. And the coefficient B then is usually known as the log rate ratio. And people take the exponent of that and call it the rate ratio. Because it's the rate ratio, because it turns out that it's the ratio of the expectations, not the difference in the expectations, it's the ratio of the expectations. And so that's what people use all the time in medical work. So if you're anything in epidemiology and everything like that, absolutely standard to use this. And then finally, and I'm doing this just because it's in the medical, in that paper on the cash transfers, for binary outcomes, yes or no, like infected, not infected. I know this is even true. This is, I think it's quite interesting. We want to transform the parameter onto minus infinity to infinity. And what do we do when we've got a parameter theta between 0 and 1? And we want to map it onto the whole real line between infinity and minus infinity. What function can we use? And it turns out the odd thing is we use this log of theta over 1 minus theta. It's known as the logit function. And so theta, what happens is that when theta is 0.5, that's 0.5 over 0.5, that goes to 0. When theta is 1, that goes to 0, that goes to 1 log. That will go out to minus infinity. And when theta is 0, it'll go down to here. And it takes this and stretches it out to the whole line. It's known as the logit transform. And so we build a logistic regression. Again, we can't estimate these coefficients exactly. We have to use numerical methods. And what we report e to the b as the odds ratio associated with the treatment. Okay, now this is just for background. These are known as generalized linear models. And we're not going to do those in detail. If we had another week, we'd be doing all these, but I don't think we got to. But if you come to them, they're really cool and very widely used. So anyway, they used the logistic regression. In that medical paper, they used a logistic regression to adjust for gender, education, age, marital status, income, socioeconomic status, etc., etc. They put all these x's in and did a regression equation and then estimated the effect of the treatment. And they got a bigger effect, 0.73. So when we adjusted for height, the effect went down. Theirs went up. Always a bit suspicious when it goes up. And they got their confidence interval. Whoa, they must have been so pleased. Look, it just excludes 1 now. So they can declare a significant result. The more I read of this paper, the less I liked it, in fact. So, I mean, it was a brave attempt. they tried to, interesting when you read, they tried to recruit 3,000 people. They obviously had a lot of trouble recruiting people, difficult study to do, and in the end it wasn't big enough. It's just not big enough to really prove whether these things worked or not. It's very it's sort of, they might, but they might not. So it's not very convincing evidence, this whole study. A lot of, must have been a lot of effort to do it, and interesting, but it's not big enough, not big enough. It just shows you need thousands and thousands of people to prove something like this. Okay, are there any questions on that? And then we're going to have any questions on that? Okay, let's have a break. Can we hand these round? Now, these are 3 stories. And we get, if we just, each table is going to get, can you do them? Each table is going to get 3 stories. And what I want you to do is to read them, maybe one each, or pass them around. Actually, we've got more than...
We've got 20.
Anyway, you can just choose one story if you want, or you could have a look and then pass it along. Okay. So these are 3 stories, and here are some questions I'd like you to think about. The first one is a picture from the Times, a graphic. And you could have a go, some people have a go at that one, and see if they can understand what it's about. I find it quite tricky. So I think it's the most incomprehensible picture I think I've ever seen. So see if you can understand what it's trying to do. This was a real picture from the Times. Here's another story from a British newspaper about a family who had 3 children, and they're all born on the same birthday, in different years, but on the same day. And here's another story about accidents in South Africa. So let me give you, I'll give you 10 minutes. So I'll give you time to look at one, make some notes on it for yourself, and then when you've had a look at it, pass it on and have a look at another one. So don't just look at one, and I'll give you 10 minutes to look through them. Okay, and we'll wander around. Have you had a look? Tutors, did you have a look at them? Yeah, okay. Well, have we can walk around. If there's any of the English that's not clear or anything like that, please ask us. And talk amongst yourselves. Feel free to talk. You don't have to do this on your own. And you're not getting marked on it. Yeah, retail banking is, if there is sort of personal customers, everyday things, like, ATMs and things. And investment banking is a sort of big commercial gambling on the future sort of thing that people do. Yeah, the picture shows 5 banks, HSBC, etc. So it's describing 5 banks. In the picture, in the Times graphic, just concentrate on the bit in the middle, the yellow and the blue, rather than the assets and revenue and things like that. Don't bother about the numbers in the corners. It's just the main picture.
I don't understand the second question. Why is it sort of like...
Well, I suppose I can't think of an answer. That's the point. I can't think of a good answer. I mean, it shouldn't be like this. It's a stupid picture. So it was a sort of question saying, well, why? It's not fair to ask it really, because it's not one I know an answer to. Because the man is an idiot, I think. Because there's no reason for it to be a pie chart. It doesn't help or doesn't tell you anything, it just confuses everything. So that's the idea. Bit of a trick question. Right. Okie doke. Have you looked at things? You okay? Yeah, let's stop now. All right. Okay. Now, right. Now, what's the best way to do this? Let's. I'm not going to make you hand anything in or not. Let's look at the. Oh, I haven't got any pictures of these up. Oh, I should have got a picture of them. Okay, let's go through them. The picture, the graphic. What is it? Can someone say what it's trying to communicate? What's the actual message there? Do you know? Anybody? Anybody willing to say? Oh, first of all, what did you think of it? Did you think it was clear and informative? No, I think it's the worst graphic I've ever seen. It's absolute competition. It's completely incomprehensible. So that's one of the examples. The first correct thing is that it's really horrible. Now, so what was it trying to say? Anybody willing to make a comment? We got a bank. The actual data. We got a bank. We got sort of 5 banks, and we've got 2 numbers. We got the percentage in retail, and there's 5 numbers there. Is this right? And a percentage in investment. Bum 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 bum. That's it, isn't it? There's nothing else. Is there anything else? No. Okay. So. What have they done? You know, they must have seen those numbers and thought, let's make a pretty picture. So the second one, why is it a sort of pi polar area chart? It's a bit like one of Florence Nightingale's ones. Are the pies the same size? Any idea why? You know, they've drawn them out like this, haven't they? And then this one is like that. But what is there something? The width of this, does it correspond to something? Can anyone see? Does it mean anything? No. Yeah, I don't think so. Yeah. Okay. Right. Well, the main thing is to extract that that's all it is. Now, how? Okay. Here's number 3. How could you better present data like that? How would you present that data? Do you think? Sorry? Yeah, with a histogram, or what you might have something like the banks, the 5 banks along the bottom, and actually, with the name, one little trick which is quite good, I think, is that when these banks have got quite long names, it's better to draw it horizontally. We haven't been doing the horizontal bar charts, but they're actually rather nice when you draw them. Newspapers use them a lot. And also the eye is very good at doing vertical comparisons. So it's actually a really good thing if they did HSBC and Standard Chartered and things like that. Okay, so there's the 5 banks, and you got this could go up to 0 to 100 or something like that. How would you do what would be the ways of putting those on there, do you think? Would you yes, okay. You could stack them. You could go retail in one colour and then investment in another colour. That's a stacked bar chart. And you'd have another one like that, which would be like that and like that. Or what's an alternative? Quite a lot of people do these. Is there something else you could do? Yes, what? Sorry? What? Oh, make them side by side. Yes, exactly. Because the other thing you'd do is to do 2 bars in different retail and investment in different colours. And I don't know, which do you prefer, that one or that one? Second one, yeah, I think so. I think this is clearer because you can, if they're in very different colours, you can naturally just look at the blue or just look at the red, and you can see the proportion between. So, really, why didn't he just do a nice little picture like that with a whole lot of bars like that? That would have been, didn't it? Okay. So, thanks very much. That was good, and it just shows that just doing the simplest, thing is often the best. Keep the junk out of it. But it's a good idea on the horizontal. Remember, the horizontal bars are good. True, he didn't actually put a number. I think what he must mean is small, or, he's not quite sure. Yeah, it's true, one of them just had nominal. So you would just put a little thing here. I don't know what you'd put, maybe a little wavy thing or something to show you're not quite sure how much it is. Yeah. Nominal means hardly worth talking about, I suppose. There's something there, but not important. Yeah. You preferred it vertically? Yeah. Like that. Yes, yeah. It's funny, there's disagreement on this. Yeah, you can never get people to agree. Yeah. The problem if you draw it vertically is the labels, the standard chart. Where do you put the name? Because you can write them sideways, but it's more difficult to write them. Get the words in at the bottom.
It's just like the same as writing the name of the month, the name of the week, just the same as
Yeah, but usually you can use abbreviations for those. Anyway, yeah, no, I think vertical. Yeah, I think it's a matter of taste, I think, whether you prefer vertical or horizontal. But anyway, just a basic bar chart is just great. Okay. The kids born on one day, 3 birthdays. Can anyone say where the 1 in 48 million came from? Anyone got an idea where that number came from? What they did was, they took, exactly, if you take 1 over 365 times 1 over 365 times 1 over 365, you get roughly like that. So that's where they got it from. Now what is their reasoning, do you think? Can someone say why did they do that? So any idea? Anyway? Yeah. Sure. Yeah.
Each year you burn 1 day.
Yeah, 1 day out of 365. Yeah. And why multiply them together? And. So remember, we multiply when we have it's the first one and that, and we get that. Okay. Is that's fine. Is that the right number? Well, do you think that's correct? What's wrong with it? I mean, and I say that the point is that these stories happen about once a year in the UK. I've got 3 of them in the newspapers. Every year there's stories in the newspapers. So it can't be 1 in 48 million because we don't have that many children born every year. So that 1 in 48 million is wrong. Why is it wrong? Richard. Oh, sorry, Mira.
Because this is the probability of 3 random people to have the same birthday. But here there are other factors in the family.
Ah, yes. Yeah. That's one point, is that and that's to do with the assumptions. The assumptions, well, essentially, the assumption is there's no family planning. We make this, we have to assume, we assume as mathematicians that babies come along at random, like that. Just for, oh look, a baby. That you don't plan it, you don't think, oh, we should have a baby in a year's time or something like that. They come along as a completely random process. So this is what we assume. And in which case, this is the same probability within the family as if they are random people. So you're right, that's probably not, it's a big assumption and probably untrue, but we are actually modeling as if it's in a random people. But there's a bigger reason, there's a more important reason in fact. That's another point, because that says, this is they're talking about the probability of one family. In fact, there are 1 million families in the UK with 3 children, with greater than 3 children. So the probability, these things could happen quite frequently. Okay, we'll come back to that. But what about the 48 million? Is there something wrong with that? The point is, this is calculating the probability of something, but not what they're interested in. You see, anyone got this? This is quite a tricky point. If I said a date, January, when were they born? February the, sorry, 27th. October 7th, right. If I said before the first baby was born, what's the chance of getting the 3 children all born on October the 7th? This would be the answer. But that's not what they're asking. They're just saying, what's the probability of 3 children being born on the same day? Not the probability of 3 children being born on October the 7th. Do you see the difference? And how would that, if we do that, how would that change this calculation? Yes, exactly. The first one doesn't matter. It's only the second 2 that provide the coincidence. The first one could have been born on any day. So what we're really saying is, what's the chance of having 2 more children born on the same birthday as the first? Now, if we say it that way, it becomes clearer that it's only this that's important. And in fact, it's only 1 in 135,000 chance. So in fact, it's not that uncommon. And there's at least what we would estimate. So how many families do you think there are in the UK with 3 children, all with the same birthday, born in different days? Somebody said something. It's about 1 million families, 1 in 135,000, roundabout. Yeah, it's about 6, 7, 8, something like that, you'd expect. Just that divided by that. And there are. Well, I think I know 5 now, I've found. 5 or 6. These happen, there's new ones coming along about once a year. This is not uncommon. Okay, so that was just, is that all right? Because it's quite a subtle point, but it's one that they always get wrong, the newspapers. Whenever they say the chance of something happening birthdays, they always get it wrong. Bit of bad probability. Okay, final thing. Any questions on that? The birthdays? Right, final. The accidents in South Africa. What did this story say? What did the... What did you think of the story? Anybody? If you go online, you find people criticizing this story, saying they didn't like it. So what did the story... The story is basically comparing, bicyclists with people in taxis and minibuses. And what was the main headline? What was it? Yeah, it's about 2% of deaths in each of them, was it? Was it 2%? Yeah, okay. So this is, of all road deaths, so about 1 in 50 people who die on the roads in South Africa are cyclists, and about 1 in 50 are people riding in a taxi or in a minibus. So the rest must be knocked over by cars or in cars or on motorcycles or something like that. Okay, and they say then cycling is as dangerous as that. Do you think that's an appropriate conclusion? No. Well, okay, why? What's wrong with that conclusion, to say that therefore they're equally dangerous? This is just looking at the number of deaths. Is there a better way to make a comparison? How else could we compare them? I mean, do you think there's as many cyclists as people riding in minibuses? I mean, do many people cycle? There's all sorts of other factors, like how long the journeys are, and the other thing is just, I think you say, how many people are doing this. So what they're not mentioning is what's known as exposure, which would be something like person miles. Person miles, which would be, how many people are doing it and how far are they travelling? So how many miles are travelled? And then you could work out which was more dangerous per mile, or per hour, or per minute, or per journey. So to make an actual sort of comparison. Because, yeah. Is that okay? Does that make sense? That you need to know how many people are doing these things in order to be able to say which one's more dangerous than one or the other. And so typically on transport, you do it per mile. You say how dangerous are things per mile, and compare transport like that. Okay, right. Let's just finish off. I've just got a couple of things to do to. Three more slides. These are just things people have asked about. So stuff we're going to do in the practical. Things people have asked about is continuity corrections. This is, I've been trying to avoid some of this sort of stuff because it's frankly a bit tedious, but the trouble is, the next two slides is all to do with the fact that this confusing business that you use one method and you get one answer, and you use a slightly different method and you get a different answer. Slightly different. And this is I realise this is really bad, difficult for mathematicians who are used to there being one answer, right or wrong. And it's just not the case in statistics, unfortunately. So the continuity correction is when, for example, we've got a binomial distribution and we make some normal approximation to it. So it looks like this, perhaps. And let's say we wanted the chance of it being, I said this is a 20, 0.5. So what's the chance of it being 13, 14, 15, 16, 17? What's the chance of, you flip a coin 20 times, what's the chance of getting 13 or more heads? So this is a binomial 20, 0.5. Now we want then this area, which turns out to be, when we add them up, 0.13. We use this sum d binom 20, 0.5, between 30 and 20, 0.13. So that area is 0.13. Now, let's say we do a normal approximation. The normal approximation, now remembering the expectation of the binomial is NP, which is 20 times 0.5, which is 10, and the variance is NP. I'm not even going to ask you this because you should know it. 20 times 0.5 times 0.5, which is 5. Yeah, I got that right. I got it wrong at first, but never mind, when I was doing it. So that's 5. So it's a normal 10, 5, and that's what I've drawn there. The simplest approximation then is to say what's the probability x is greater or equal to 13 is about, you take away the mean and divide by the standard deviation on each side, 13 minus 10 over root 5. This is now a standard normal, so we can look this up in the normal tables, or we use Q norm or P norm. I never remember which, P norm. And we get 0.09, which isn't very good. It's not a great approximation at all. So that normal approximation isn't very good. The thing, but what we've done actually, if you think about it, is that if you consider this as a continuous thing, this is where 13 is, and we've just calculated this area. When we consider this as a distribution, we haven't had half of this, we haven't counted up. So what you have to do to get a better approximation is to integrate it from 12.5, from 12.5, which means then we will be adding up all of this as well. And that should be a better approximation. Do you see that? That it's a problem with approximating a discrete distribution, which are lumps on 13, 14, and 15, with a continuous distribution. So when we do that and put 12.5 in there, we get a fantastic approximation. It's unbelievably good. Just by moving the thing back a half. And so that's what continuity corrections do. So when in R it says continuity correction, it's done something like that for you. It's controversial. I don't like these. I don't think they should be doing these. So I don't like continuity. I disagree with continuity corrections on principle. It's because it's how you define a p-value for a discrete distribution. This is a technical thing, but I actually like a mid p-value, which is the probability of it being greater than that, plus half the probability of it being equal to the point. So it'd be that plus that, which is what you get without the continuity correction. So there's no right or wrong about this, I'm afraid. Okay, so I hope that's a bit clearer. Now finally, t-tests. This is the other thing that, when we're comparing things, you put it into R, into the t-test function, and it'll give you test and p-value and confidence interval, but it's not based on the normal distribution. It's based on the t-distribution. And the reason for that is that if we're estimating these variances, in a sense, this should be slightly bigger to allow for the extra uncertainty in the variances. This 1.96 gets slightly bigger. But there's all sorts of different t-tests. R does one. The Welsh something, we'll do it in a minute. It does this t-test, which I'd never seen before, but it does a sort of t-test. And so if we just want to know whether they're from the same population, the same mean, we can use this approximate confidence interval, but we can also use the t-test. And that will generate intervals and hypothesis tests. Now it is better to use the t-test, so that's not really arguing. It is better to use that, but it doesn't usually make that much difference. So you're going to do an example like this now when we go up, but on the UN data. So say, for example, if you want to see men taller than women, this is a trick. If you just want to use complete cases, you can do na.admit to the entire database. The entire database. If you do that, it just takes out all the cases with anything missing. It just removes anybody with anything missing. It's a really neat instruction in one line. And the other trick, which is on the practical sheet, is if you want to select heights of men, you can just do height square bracket gender equals double equals, that means logically equals to m, and it'll just pick the heights of men, and that'll just pick the heights of women. It's a way of selecting cases. And then you just do t-test. Easy peasy. And it'll give you a t-value, degrees of freedom, which they estimate in some way, and they get a p-value 0.035. So the men are significantly taller than women. And here's a 95% confidence interval. So this is, in a way, more correct than the simple normal approximation, but not usually that much different, and unless the sample is really small, like 5. So I get you to do both in the practical. Okay, so those are there for you to look at, but we're going to do those in the practical. Any questions? Any questions? Oh, yeah. No, there's all sorts of ways you could do this. You could do, well, you don't need the dollar because by doing the attach, I've got rid of the first part of the data frame. There would be other ways to do this. This is the way I usually do it. But I'm sure there will be other ways to do this, to select the cases. And you could try them out. Okay, is that all right? Okay, as I said, there's a practical class.